Okay, so today we're going to kind of talk about more properties of antiderivatives, or not properties of antiderivatives, but we're going to put antiderivatives to use in a sense that we did for derivatives, such as, let's look at our first example. So for example one, we're going to say graph the antiderivative of the function below given that f of 0 equals to 2. So basically for this problem, what we're doing is I'm going to give you a graph of a function, and we want to graph its antiderivative, and we're told that the antiderivative starts at this point. So this kind of gives us a starting point. So um, let me give you the function that we're trying to graph the antiderivative of, which would be this one. Okay, so and this kind of tapers off. So basically, let's kind of describe this. So what I'm saying is this is the graph of the derivative, and I want to graph its antiderivative. So we're kind of working backwards here. Because look, so what do I know about my function? If my derivative is negative, that means the original function is decreasing. So what I know is that when I graph the antiderivative, from 0 to 1, it's decreasing, and then from 1 to 3, it's increasing because it's above the x-axis, and then from 3 and on, it's always decreasing, but notice as x goes to infinity, this gets closer and closer to 0, so it decreases at a slower rate. Okay, now, with that said, we know where its antiderivative is increasing and decreasing. Now, at x equals 1, we have a minimum. At x equals 3, we have a maximum. How come? Because it changes from decrease to increase, and then it changes from increase to decrease. Okay? And then the last thing I need to pay attention to are intervals of concavity. So what do I know? If the slopes of my tangents are positive, or if f prime is increasing, then that means my second derivative is positive, which means the original graph, or the antiderivative, this should be concave up. When the derivative is decreasing, or if the slopes of the tangent lines are negative, then that means the antiderivative of this guy is concave down. So what do I know? From here to here, this is increasing, which means my slopes are positive, so its antiderivative will be concave up. Over here, I have an inflection point because what do I notice? It changes from increase to decrease, which means the slopes go from positive to negative. And then I have another inflection point here. So what do I know? Concave up from here to here, concave down from here to here, and then concave up the rest of the way. So the way this is going to look is as follows. We're going to start, and I'm going to try to kind of number or label these in a way where they're right above each other so it'll be easier to graph. So I know I start from 0, 2, because that's what we were told. At x equals 1, what am I going to have? I'm going to have a minimum. At x equals 2, I'm going to have an inflection point. So what do I know? From 0 to 1, it's going to decrease, and it's concave up. And it's concave up all the way until x equals 2. So I hit my minimum all the way until x equals 2, it's concave up. And then what happens at 2, it changes concavity, because notice how my slopes of tangents go from positive to negative, but it's still increasing all the way up until 3. And then after 3, it's decreasing. So it's concave down, and it's increasing all the way up to x equals 3. And then what do I notice? From x equals 3 to x equals 4, it's still concave down, but in after 4, it becomes concave up because the slopes of my tangent become positive. So it's decreasing, it's concave down, and then at x equals 4, I hit another inflection point, which then it becomes concave up, and it's decreasing, but the further I go down, it decreases because the y values of my derivative are getting closer and closer to 0, which means this guy's still decreasing, but it's decreasing at a slower rate. So it looks something like that. So notice how I was able to obtain the graph of the antiderivative, which looking at its derivative. So these are my minimum, maximum, my inflection points, and so there you have it. I graphed antiderivative. If you remember, We did something similar to this on the last exam. Okay, so that's kind of what's going on here. So now let's move on to direction fields, and then that'll basically wrap up this section. So we can also, at times, draw direction fields. And when I say direction fields, I'm literally just talking about the slopes of the tangent. So this consists of slopes of tangents. Okay, so I'll kind of show you what I mean by what a direction field is. To graph the antiderivative of a function. Okay, so one comment I want to make here. Why are direction fields so kind of advantageous or helpful for us? See, for the last example we did, I gave you the graph of the derivative and I asked you to graph its antiderivative. Now, what if I give you a very complicated looking function and I ask you to graph its antiderivative? And so sometimes you say, look, instead of having to graph the function so then I could graph its antiderivative, why don't I use the idea of direction fields? Because direction fields kind of help us see exactly what's going on. So let me kind of give you an example here where we'll make a direction field and we'll go from there. So for example 2, we'll say if f of x equals to square root of 1 plus x cubed minus x, I want you to sketch the graph of the antiderivative of f that satisfies the initial condition f of -1 equals to 0. Okay, so first of all, if you notice, the domain of this guy is what? From -1 to infinity. So we're kind of starting there and we're moving to the right. But here's the thing. To graph the antiderivative of this guy, the first thing I would probably need to do, or if I were to take the approach of example 1, I would graph this guy, and then I would try to graph its antiderivative. Now, if you look at this, this might not be, it's not that we can't graph this, we can graph it, but it might not be a good-looking function to graph. So I could say, look, instead of trying to graph this, I could avoid that by using the idea of direction fields. So we're going to use direction fields. Now, what do I mean by a direction field? The slopes of the tangent lines would give us an idea as to what the direction or what the derivative or antiderivative of this guy will look like. Okay, so basically what I'm going to do, starting from x equals -1, I'm going to find the slopes of this guy. So remember, after all, I'm trying to sketch the antiderivative of this guy, which, what does this mean? Whatever capital F is, this guy is its antiderivative. So the slopes of the tangent lines of this guy describe the derivative of that guy. So what we're going to do now is, if we're going to make a direction field, is here's what I'm going to do. I'm going to start from x equals -1. And what do we know? As long as x is -1, what are the slopes of the tangent lines of this guy going to look like? Well, how do we figure that out? We plug in -1 here. Okay, so if I plug in -1 into x, so if I come off to the side and say f of -1, which gives me 1 minus 1 minus -1, which these cancel out, and what do I get? I get a slope of 1. So what that means is when x is -1, the slopes of my tangent are always going to be 1. So let's just draw the slope of a tangent line that has a slope of 1. So that looks like it has 1. And basically what I'm doing here is when I draw these multiple slopes are saying, look, I don't care what the y value is. As long as x is -1, the slopes of my tangent are going to be 1. So these all have a roughly a slope of 1. So now let's try x equals 0. So if I plug in 0 here, what do I get? I get square root of 1 plus 0 cubed minus 1, which just becomes 1 minus 1. It becomes 1 minus 1. The cube root of 1 on this should be 0, not minus 1. So I get what? 1 again, which is weird. So if you look at this, it looks like when x is 0, the slopes of my tangent are also 1. So when I see this, I kind of say to myself, well, what happens between -1 and 1? Is it staying constant, or does it kind of, what happens at -1/2? So I kind of would want to check what happens at -1/2 to see, do the slopes of my tangent really stay constant from -1 to 0, or is there something else going on here? So if I plug in -1/2, what do I get? I get square root of 1 minus 1/8 minus 1/2, or 1/2 minus 1/8, right? And then square root of 1/2 minus 1/8, that becomes, what would this be? This would be 3/8 minus 1/2. And so what does that give us? Let's see. If I were to grab the calculator just to put it in so we see what that looks like. So if I were to say the square root of 3/8 minus half, that gives us about 0.11. Oh, I'm sorry, it shouldn't be 0.11. This should be a plus 1/2 because I plugged in -1/2. With this minus and a negative makes it plus. So I should actually put square root of 3/8 plus 0.5, which gives us about 1.1. So it's slightly increasing faster. So the slope would be a little steeper than what's going on here. Okay, so I'm just trying to draw these slopes. So what do I know? It's increasing at this rate. It picks up a little bit and then it slows down again. Okay, so now let's try x equals 1. If I plug in 1 into the derivative, what do I get? I get rad 2 minus 1, and rad 2 minus 1 is roughly 0.41. So the slope becomes less steep, so it kind of does this. So it's a little flatter. Okay, and then at x equals 2, we do the same thing. So I hope you guys are understanding what I'm doing here. I'm just drawing slopes of a bunch of slopes of tangents, because that's what pretty much this whole idea of direction fields are. So if I plug in 2 for x into the derivative, I get rad 9, which is 3 minus 2, which gives me 1 again, so it becomes steep again with a slope of 1. And then let's do it for 3, and then we could stop there. So if I plug in 3, what do I get? F of 3 gives us square root of 28 minus 3, and square root of 28 minus 3 is roughly 2.29. So we see it starts getting steeper and steeper. So now we could see kind of what it behaves like. So here's the thing. This direction field basically tells you what the shape of the antiderivative should look like. So now this is saying that at x equals -1, my starting point is 0. So if I use a red pen to do this, if I start at 0, what is this saying? It's increasing, my antiderivative is increasing, and then it kind of slows down a little bit, and then it starts increasing again. And so there you have it. I just, using the direction field of this guy, I was able to use the slopes of the tangents to get the shape of the antiderivative, which hopefully this makes sense to you guys. If it doesn't, let me just give you one more example, and then we can basically stop here. See, if I were to say, look, here's the graph of x squared. The slopes of the tangents to this curve at each point, which is pretty much the derivative, don't the slopes of the tangents kind of, or not kind of, they in fact do, don't the slopes of the tangents give you the shape of the antiderivative, which is the parabola or this quadratic function. So that's basically what we're doing. So instead of graphing this guy and then trying to graph its antiderivative, what I did was I said, look, at each x value, these are my slopes of the tangents. This is how they look, and I plugged them in to find them. And then using the slopes of the tangents, that just tells me how fast the antiderivative is increasing at each x value, which allows me to kind of, as long as I'm following the direction field or the slopes of the tangents, that'll give me a general idea of what the antiderivative looks like. Okay, so basically that's what this section is all about. So we're done with, or the second half of section 10. So we're pretty much done with section 10. So now you should be able to complete the rest of the home problems. If you have any questions, don't hesitate to ask me. And I also have a worksheet for you, or a handout. It's not a worksheet, a handout that'll kind of help clarify these slope fields or the direction fields that we talked about today. Okay, so that's basically it.